Right now we're going to look at logistic regression and try to build a conceptual understanding of how it actually works. First off, logistic regression is actually a binary classification model. So if you have a task where you want to classify whether a student is going to fail or pass based on their marks, you could use this model. The core function of this model is the sigmoid function, which scales any number from the real domain negative infinity to positive infinity into the domain 0, 1. Since probabilities only exist from 0 to 1, right? There's no negative 2% probabilities. There's no 150% probabilities. There's either 0% or 100% or anything in between, right? So the 0 to 1 scaling is pretty useful in that sense. And since we have a lot of values that are scaled between 0 and 1 and not strictly 1 and 0, we have to apply a threshold value. What this does is, suppose our threshold is 0.5. If we get our output of this function as 0.6, we can scale it directly to 1 because it lies above 0.5. And suppose the value is 0.4 and it lies below 0.5, we'll scale it to 0. So our final outputs after all the calculations are either going to be 1 or 0. The z value here basically takes all their inputs and their weights and adds them together after taking their respective products, and that's plugged into the sigmoid function here. Now let's look at how the scaling actually works with different z values. In this context, it's referred to as an x value, but yeah, it's the same concept. So we plug in a negative 3 value here, we get 0.047. We can plug in a positive value as well, like 5. We get 0.99. So again, both values are between 0 and 1. No matter what value you plug in here, it's always going to be between 0 and 1. Now you might be wondering, why can't we just use linear regression models, right? The problem with linear regression or polynomial regression models is that the output is going to vary beyond 1 or beyond 0. So you can get 2, 3 or some other value, which is impossible in a probabilistic sense, right? Like we've said, we can't get 200% or 300%. We can get only 0%, 100% and everything in between. So for scaling from 0 to 1, logistic regression using the sigmoid function accomplishes this properly. Now let's look at a small code implementation to visually understand how this works. First, we import numpy and matplotlib. Numpy is for dealing with numbers, matplotlib is for visualizing. So we set a checkpoint here with number 42, and we first initialize the x coordinates of the scatter points, right? So we need either 1 or 0 labels. The 1 labels and the 0 labels have x and y coordinates, and these are the x and y coordinates, marks and outcomes. So np.random.randint initializes random integers from the range 30 to 100 with 30 points in total. So for the outcomes variable, first we pick 30 random points and multiply by 10. What this does is, initially the mean and standard deviation are 0 and 1 respectively. Because the mean is 0 and the standard deviation is 1, we need to scale it up because 1 as standard deviation is not realistic. And so we multiply it by 10 and now it spreads a little better. Our threshold here is 60. So any value, any random integer here that falls above 60 is directly scaled to 1, and any random variable here below 60 is scaled to 0. And along with that, we add the marks so that the marks can be a proper baseline as an intercept, and all these other, this section of the code can basically help the data spread a little bit more. Our return type is specified here to be an integer, because even though this seems like it's an output as an integer, it's a comparison function. So your return format is going to be a true or a false. So a Boolean output. Next, we define the sigmoid function as we've seen here. This one is a sigmoid function, and this is what we code in that small block here. Next, we specify an intercept and a slope. We're not calculating the slope and intercept here, but we look at the loss function later. But yeah, we specify the slope and the intercept here, and our x value, which is our x variable here, is going to lie in the range 30 to 100 and have 300 points. Right. The y value is going to be the sigmoid function of this input. So this negative z here is what we calculate here. So our x is here, our w is our slope, and our intercept is our b. Next, we just scatter the marks and outcomes. Right. Next, we also plot the sigmoid curve that we've calculated using the slope and intercept that we ourselves have provided. Note this, because we're not calculating the slope and intercept here using a loss function. We're just using this code for visualization, right? So we plot the sigmoid curve as well along with the points. We've looked at the visual demonstration of how the sigmoid function works and how logistic regression actually inputs a linear equation and converts it into a 0-1 domain, right? But now let's look at how this weight and bias is actually calculated, right? So first we initialize a random weight and a bias, and next we have to keep on correcting it with every iteration. So how do we do that? We do that using a log likelihood function. So this is a log likelihood function which basically rewards every correct guess with a higher probability and penalizes the wrong guesses with a lower probability. So yi here is basically the class of 1, so the true class, right? So yi here being 1 means this section of the formula entirely gets deleted and it does not survive, because 1 minus 1, 0, multiplied by anything, 0, right? Next up, what we do is we multiply yi, 1, with the log of p cap I. P cap I is the value that we get here. So computing with a normal z value, we get this value as p cap I. So the higher our p cap I value is, the penalty is lower, because the log of 0.9 is higher than log of 0.1. Log of 0.1 would be something around negative 2.3. Log of 0.9 would be something around negative 0.1. Right. So the higher this p cap I value is, the better it is for our model. And suppose our yi value is 0, right? So this section of the formula gets negated and our true label completely is destroyed, and our false label is rewarded. 1 minus 0 will remain 1, and so this section of the formula now remains, right? So here we subtract p cap I from 1, because in the case of the class being 0, suppose we get 0.9, the value here is going to be 0.1, and again our penalty is going to be negative 2.3. But if we get 0.1 as our output here, we are going to get our penalty value as negative 0.1, since we are subtracting, right? So in both cases, our p cap I value is desirable to be higher so that our penalty is lower. And yeah, that's basically how the error function works for logistic regression, and how weights and biases are updated, so that suppose our weight and bias keeps iterating for a while, it's going to get to an optimal amount where we can figure out a good steepness of this curve and fit of this curve. And then we can figure out a threshold and figure out who's going to pass or who's going to fail. So basically we have a linear equation that consists of all the inputs along with their weights. We take their output z and plug it into a sigmoid function to scale it between the range 0 to 1. Now we have a sigmoid curve that fits probabilities, and we can also assign a threshold so that we can strictly classify each output to 1 or 0. And I hope that you understood that there's a lot of applications to this. Suppose you want to build a detection model of whether something actually exists in a picture or whether it doesn't, then you'd use this model, right? Because again, it's a very good binary classification model. So yeah, keep learning. Curiosity is the only thing that's got us this far, and I'll see you guys in the next one.